Hello dear students, today I will start third unit, that is convergence of sequence and series. Okay. Generally, main target is testing convergence and divergence of series, infinite series. Okay, so infinite series, for first of all, sequence. What is sequence? How we know sequence? You know from your previous class, sequence, number of succession of numbers, succession of numbers or terms. Okay, succession of numbers or terms, sequence. Just like this, suppose 1, 2, 3, 4, 5 and so on up to 100. This is numbers which are following some rule, that numbers, succession of numbers following a rule, that is each number is one greater than the previous number and first number is 1. This sequence. Here number of element is finite, so it is finite sequence. If the number of elements is infinite, then we can say that this is infinite sequence. So succession of numbers or terms which follow some rule, here for what its terms of sequence, that is un, is what? N, where n belongs to natural number, from 1, 2, 3, 4 up to these are the numbers. If un equals to, suppose 2n minus 1, then un means nth term of the sequence. Just putting n equals to 1, then you can get first element, second element, third element and so on. So here un equal to this, that means what? u1 equals to what? 2 into 1 minus 1 equals to 2 minus 1 equals to 1. u2 equals to 2 into 2 minus 1 equals to 4 minus 1 equals to 3. u3 equals to, just put the value small n from 1, 2, 3, 4 and so on. So here 1, 2, 3, this is first element, second element, third element of the sequence, terms of the sequence. So u1, u2, u3, and similarly u3 equals to what? 2 into 3 minus 1 equals to 6 minus 1 equals to 5. So we can find nth element is what? 2n minus 1. If n tending to infinity, then you can get infinite elements. So we can get sequence as what? 1, 3, 5, 7 and so on. Nth term is what? 2n minus 1 and so on up to infinite. This is infinite series, the sequence. Okay, so this is nth term. So nth term is a function of n. We see nth term is a function of n, always, of a sequence. So sequence is It is succession of numbers or terms which follow some rule. Rule is this. Rule. So we can say sequence is a function of natural number n, real valued function. In other words, we can say sequence is a function from set of natural number to real valued function. Okay? That is un is a function of n. Un is equals to function of n. And sequence is denoted just like this. Nth term, if you know nth term in terms of n, so we can write this n equals to 1 to infinity. Here n equals to 1 to infinity, just in sequence and finite sequence. We are also concerning always infinite sequence, infinite series. Okay, because our main target is what? Identifying whether the sequence is convergence or divergence, infinite series is convergent or divergence. Our main interest is to find out the nature of the series, whether it is convergent or divergent. So this sequence we can also write like this: n equals to 1 to infinite. Okay, also you can write like this: un n equals to 1 to infinite. All are sequence. Okay, the notation for sequence. Sequence denoted by this. Okay. So here un is nth term of the sequence. Now, what is limit? Now, limit of sequence. Limit of sequence is identifying by its nth term limits. If this is a sequence, suppose this is a sequence, then if, then limit n tending to infinity with un L, and then limit of sequence is L. Okay? If nth term tending to L, that is un tending to L, nth term is what? Nth term of sequence. So if this is tending to L as n tending to infinity, here limit, always limit will be find as n tending to infinity. If un tending to L as n tending to infinity, then the limit of sequence is L, and we are denoting like this. Limit of sequence is L, and we are denoting limit n tending to infinity n equals to L. Okay. Now, convergence sequence. What is convergence sequence? Convergence of sequence. Convergence of sequence. When we say that a sequence is convergent, how can we identify the sequence is convergent or divergent? So here, if limit of sequence is finite and unique, limit of sequence L is finite and unique, then sequence is called convergent. sequence is convergent and converges to the limit, to the finite limit. If limit of sequence is finite and unique, then we say that the sequence is convergent and its limit is sequence is converges to the finite limit. Okay, convergence. If limit is infinite, then divergent. If limit is infinite, plus infinitive or minus infinitive, but unique, by plus infinitive or minus infinitive, but unique, then sequence is called divergent and diverges to either plus infinitive or minus infinitive. Divergent. Okay, and if limit is not unique, either finite or infinite, then we say the sequence is oscillatory. If first point, second point, and third point, if limit is not unique, either finite or infinite. If limit is not unique, either finite or infinite, means maybe limit 1 minus 1, 1 minus 1, 2, and so on, and maybe limit plus infinitive, minus infinitive, both, then limit is not unique, and then sequence is called oscillatory sequence. Okay, so here convergent sequence, divergent sequence, oscillatory sequence. Clear? So three type of cases are there: finite limit, unique, convergent; infinite limit, unique, divergent; and finite or infinite, not unique, either finite or infinite, called oscillatory sequence. So this is main thing about convergence divergence of a sequence. Okay, so here convergence sequence means what? Limit of the sequence is finite, and we can take example just like, suppose we are having sequence like this: 1 by 4, 1 by 16, okay, 1 by 4, 1 by 9, 9, 16, and so on. It's in a term, it is very clear that this is an infinite sequence. Okay, its nth term is what? This is convergent or divergent? Just we have to check it. nth term. What? For example, this is an infinite sequence. Un equals to 1 by n square, 1 by 1 square, 1 by 2 square, 1 by 3 square, 1 by 4 square, and so on. So it tending to 0 as n tending to infinity. This means limit. Its limit. Limit n tending to infinity un equals to, or you can write like this, or also limit n tending to infinity un equals to 0, because n tending to infinity, n is in the denominator and n is square. So n tending to infinity means 1 by n square tending to 0. So this is what? Sequences convergent. Okay. Here limit is finite. So sequence is convergent. Clear? Here we see that sequence 1, 3, 5, 7 and so on. This is sequence. And its nth term, what? We can write like this. Because nth term is taken just for n equals to 1, you will get first element. For n equal to 2, second element. So from here you can get. So here un is what? 2n minus 1. It is clear that this is tending to infinity, as n tending to infinity. Implies sequence is what? Divergent. Because infinite limit is there. Okay, suppose we are having a sequence just 1 minus 1, 1 minus 1, 1 minus 1. This is a sequence, an infinite sequence. Its nth term can be written as un equals to minus 1 to the power n. Here we can write n plus 1, because u1 equals to minus 1 to the power n plus 1 means 1 plus 1. So what? This is equals to plus 1. Okay? Plus 1. u2 minus 1 to the power 2 plus 1 minus u3 minus 1 to the power 3 plus 1 equals to 1. So 1 plus minus 1, 1 minus 1, 1 minus 1, 1 minus 1. So nth term is this. Here we see that the value of limit, for finding limit, here limit un, where un equals to what? Minus 1 to the power n plus 1. Limit n tending to infinity un is equals to 1 if n is odd, and if we take just like this, and minus 1 if n is even, if we write like this. Okay, but for odd always you get because odd then this will be even, so plus, and if even then this will be minus 1. So both are limit but not unique. Here limit is not unique. Here limit is not unique. Limit is finite but not unique. Finite but not so this is not, so it is oscillatory sequence. It is oscillatory sequence. Okay, if you take here only n, then for n equals to 1 we get, if n is odd then always minus 1. So here this sequence, if we take this sequence, then here you can write even, odd. Here also we can see that limit is 1 or minus 1. That is limit finite. Limit is finite but not unique. So it is oscillatory sequence. Okay. So these are the type nature of a sequence. So whether sequence is convergent, divergent, and oscillatory, we can identify. Now, just we will try to find the technique by adopting which, how can we identify the whether sequence is convergent or divergent. Here 2-3 things are important, just like bounded sequence. Bounded sequence, if un n equals to 1 to infinity is such that un is less than k for all n, where k is a real number, then we say that sequence is bounded. Bounded means nth term is always less than k. That means there is a number which bounds the value, its value. Its value is less than k. Okay? This is for bounded sequence. Okay. Maybe positive side boundary, maybe negative side boundary. By taking modulus, you can see that. Means un is bounded by some numbers. Then we can say the sequence is bounded. Okay? And monotonic sequence. What is monotonic sequence? Monotonic sequence. Monotonic sequence means either increasing or decreasing. Either increasing or decreasing. Either increasing or decreasing means, just you can see, either increasing or decreasing means only increasing, then we can say the sequence is monotonic sequence. Only decreasing, then you can say sequence is monotonic sequence. But both together, the first increasing, then decreasing, and then increasing and then decreasing, increasing, decreasing. If this type of nature is, then we can say that is not monotonic sequence. So, for example, 1, 4, 7, 10, and so on. This is monotonic sequence. This is increasing sequence. You can write also 1, 2, 3, 4, 5, and so on. This is increasing sequence. Increasing sequence. Decreasing sequence 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5. What? Decreasing sequence. This is decrease. This is decreasing sequence. This is increasing sequence. All are monotonic sequence. If sequence is monotonic and bounded both, then here we see that 1 by 2, 1 by 3, 1 by 4 here in this sequence is bounded because its nth term. What is its nth term? 1 by n, un equals to 1 by n. Always less than equal 1. Okay? Less than equal 1. Because 1 by 1 is equal 1 by 2 less than, 1 by 3 less than, 1 by 4 less than, 1 by 5 less than. That is n is greater than equal 1. Always we know. So 1 by n is what? 1 by n is this is un. So un is less than equal 1. So boundary. So this you can write like this also. Bounded sequence may be equal. Okay, like this. So this is bounded and monotonic. So it is convergence sequence. Also we see that un 1 by n tending to 0. Convergence sequence. So every monotonic and bounded sequence is convergent sequence. Okay, bounded and also monotonic. Then, so here we can see that if here we see that 1, 2, 3, 4, 5, 6. This is not bounded because there is, if we find a large number and all the elements are less than that, then I can also find another large number because this is increasing, not bounded. This is also increasing, not bounded. All are monotonic sequence, but this is monotonic and also bounded. So it is convergent. So here we find a rule that if a sequence is monotonic and bounded, then sequence is convergent. So we can say that every monotonic and bounded sequence is convergent. Okay? Every monotonic and bounded sequence is always convergent. Clear? Every monotonic and bounded sequence is always convergent. This is a rule. By using this, if we know the sequence is monotonic and also bounded, then we can say sequence is convergent. Okay. Here monotonic, this sequence is not monotonic. This is not monotonic. 1, then -1, 1, then -1, not increasing, not decreasing. So this is not monotonic sequence. Not monotonic sequence. It is not either not decreasing and also not increasing. So it is not monotonic sequence. Clear? So now we know that what is a sequence and how can we find the nature of sequence, whether it is convergent or divergent or oscillatory, for finding limit of its nth term. Okay, and also if sequence is monotonic and bounded, then we can say the sequence is convergent. Here now series, our main topic, that is some special limits are useful, very important. Just like this, we know 2-3 limits are like this: limit n tending to infinity, 1 plus 1 by n equals to what? E. Okay, this type of limit, also limit n tending to infinity, n to the power 1 by n is equals to limit n tending to infinity, n to the power 1 by n equals to 1. This is 1. This is 1, and etc. There are different type of some special limits. So these are the list. Okay, remember it, because for testing convergence and divergence of infinite series, we will require this limit, this type of limit, for writing some special limits. These are the special limits, very useful for solving questions. Okay, so remember all these limits. Okay, so here limit means just as n tending to negative. Whether we are trying to find the limit of an term, that means what? Limit as n tending to infinity. Always as n tending to infinity. Okay, so these are the special limit. Remember these limits, always very useful for solving infinite series, finding the nature of the infinite series, whether convergence or divergence. These limits are very useful. Okay, now our main thing is what? Series. What is series? Okay, so series, you know from your previous class also what is series. You know arithmetic progression, geometric progression, harmonic progression. They are series, a special type of series. So also there were limits of nth terms. So here series means what? If u1, u2, u3, un, this is a sequence, then u1 plus u2 plus u3 and so on plus un and so on, this is called series of terms of sequence. Series of terms of sequence, that is and is denoted by sum of n equals to 1 to infinity un, means nth term. Just if this is sequence, just add all the terms of the sequence, you can get a series. If sequence is finite, then finite term. If there are finite terms, then series will be finite. If they are in infinite terms, series will be infinite. And infinite series, generally we are concerning with infinite series, because the nature of finite series is always convergent. So here finite series, infinite series is this. Denoted notation for n equal to 1 means 1 plus this for summation. This, or you can write only summation here. Here it is clear that n equal to 1 to infinity in this case. Okay. So this is infinite series. Now, for determining whether the series is convergent or divergent or oscillatory, what will be the procedure? This is for sequence. For sequence we know as even tending to finite and unique, then convergent, infinite, unique, then divergent, and if finite or infinite but not unique, then oscillatory. But here, for identifying whether series is convergent or divergent, so for that, to determine the nature of series as whether it is convergent or divergent or oscillatory. We make partial sum of series as Sn equals to un plus u2 plus okay. We know this is sequence. This is series. U1, U2, U3, U4, U4 are what? Terms of series. They are added. But Un is nth term of the series. So nth term. So just take from infinite series, just take n terms and sum of it. That is partial sum. And after summing it, we can get also a function of S. So this can be treated as a sequence of partial sum. If, because it is also function of n, if sequence of partial sum, that is, if we make a sequence Sn, n equals to 1 to infinity, if we treat Sn is a sequence, if sequence of partial sum is means first of all we have to prepare partial sum for the sequence, the series. If sequence of partial sum, this sequence is convergent, then series is convergent. That means Sn tending to finite and unique limit, then series convergent. If partial sum sequence is convergent, then series is convergent. If this is divergent, if partial sum sequence divergent, then series is divergent. So the nature of series is determined by the partial sum, sequence of partial sum. If sequence of partial sum is convergent, then series is convergent. If sequence of partial sum is divergent, then series is divergent. And if this sequence is oscillatory, then series is oscillatory. Also, okay. So series convergence divergence when if Sn n equals to 1 to infinity is oscillatory, then series is oscillatory. So convergence, divergence or oscillation of the series depends on the convergence, divergence and oscillation of sequence of partial sum. That is, we can say that is if Sn tending to finite and unique limit, finite and unique value, then convergent. And if Sn tending to infinite and not unique, then this is divergent. If infinite and unique value. Unique value is here also unique value. If Sn tending to finite or infinite value but not unique, then series is oscillatory. Okay, Sn tending to finite and unique value, then convergent series. And Sn tending to infinite and unique value, then divergent. If Sn tending to finite or infinite value but not unique, then summation union is oscillatory. And whether a series is convergent, then we say that series converges, the summation of the series is equals to the limit of the partial sum. Okay? Whenever a series is convergent, we say that sum of series is the limit of Sn. That is, if Sn tending to L as n tending to infinity, then summation un equals to L, where Sn equals to u1, u2, un. So this is the meaning of convergence or divergence or oscillation of a series. When we say that the series is convergent, divergent, oscillation, just make partial sum for the series and find its limit. If its limit is finite and unique, then series is convergent, and limit that finite value is equals to sum of the series. If this limit is infinite but unique, then we say that series is divergent and sum is infinite. And when the series is Sn is tending to finite or infinite but not unique, then we say that series is oscillatory. Okay, so this is the convergence divergence of infinite series. How can you identify whether the series is convergent or divergent? Okay. Now our target is what? For investigating whether the series is convergent or divergent by different type of rules. Okay, so here we see that what we have to do, just find partial sum and then find its limit. So here some simple type of properties are also important. If we see that if in infinite terms the series has infinite terms, then if we delete or ignore some terms, suppose 1 plus 2 plus 3 plus 4 plus 5 and so on are infinite terms. Summation un equals to this. This is un equals to what? N. From this series, infinite series, generally we can see that it can be taken as exams that if we omit some terms, finite number of terms from this series, then there will be no effect in the convergence divergence of the series. If we add some finite number of numbers to here, some finite addition of some finite number, we add this in this series, then also there will be no effect on the convergence divergence of the series. Okay, so we can add some finite numbers to the series, or we can also delete, so there will be no effect. Okay, and also we can see that if for nature, because for infinite series is there and we are trying to find nature, whether it is convergent or what, divergent. Convergence means maybe it can be summarized to a number. Divergence means cannot be summarized. So whether the nature, it may converge or may diverge. So for identifying that, just if we suppose this is infinite series is convergent, then if we multiply each element by a constant, then also it will be convergent. If divergent, then it will be divergent after multiplying each term by a constant. So these are the simple properties of series. It can be taken as exams because this will helpful sometimes for solving questions. We may add some numbers, finite numbers, delete some finite numbers, omit first term or second term or third term. For writing nth terms, sometimes we are deleting one or two terms from beginning. Okay, and for maybe for multiplying by some constant to the element. Okay, so these are the general properties. So remember this. Okay. And here take an example. Suppose take a questions. How can we identify the convergence divergence of a series? So here suppose we are having sequence like this. One series. This is series summation n. Here un equals to what? N. We see So partial sum will be what? u1 plus u2 up to un, that is what? 1 plus 2 plus 3 up to n for this infinite series. So we know the summation n plus 1 by 2, the sum of first n natural number. So this tending to what? Infinity, as n tending to infinity. Very clear, because denominator 2, numerator n plus 1. So n tending, this n tending to infinity, n tending to infinity, this tending to infinity. This tending to infinity, it is not, this series is not convergent. Okay, so series is divergent. We can write series is divergence. Therefore, series is clear. This is divergent because Sn tending to infinite. So divergent series. Series is divergent. Sn is partial sum. Okay. And suppose series 1, 1 by 2, 1 by 4, 1 by 8. This is series. This is a series. So what you can say about it, whether it is divergent or convergent? This series. So here nth term. Here un equals to what? 1 by n square. Very clear, 1 by n square. Okay, so we can find partial sum. So here just what we do, u1 plus u2 plus and up to 1 by n square plus and so on. But Sn equal to this. But finally we do what? Sn tending to what? Tending to what? As n tending to infinity. Sometimes value of Sn finding is typical. Okay, is difficult. So sometimes we can use another method also. If we know, how can we find the sum of the series? Because arithmetic progression, geometric progression, there are very special series, geometric progression, arithmetic progression, harmonic progression. So geometric progression, we know infinite geometric progression, sum of infinite geometric progression. What is formula? A upon 1 minus r. If infinite series is this, ar square up to infinite. Then if infinite series, geometric progression, we know common ratio is there. This upon this r, this upon this r, this upon this r, common ratio r. Then its sum is this. Sum is this, a upon 1 minus r. Where r is less than 1. R is less than 1. This is geometric progression, infinite geometric progression, we know. So here, sometimes, if required, because here, 1 plus 1 by 2 plus 1 by 4 plus and so on plus 1 by n square. Finding this value as a function of n is some typical. So we can use another method, whether Sn tending to what. So here we can use this for this infinite series. Infinite series taking means n tending to infinity. So we can write like this. This up to infinity. Sn equal to this. That means what? Here n tending to infinity. So it's value what? 1 by 2 plus 1 by 3 and 1 by 4 and so on. Infinity 1 upon 1 minus half as formula a upon 1 minus r sum. Okay, so this as n tending to infinity here. infinite series, if we take as an infinite series, then its sum can be summarized like this. And this is equals to what? 1 upon 1 by 2. That is 2. That is 2. Implies Sn tending to 2. Sn tending to 2. As n tending to infinity. As n tending to infinity. Because n tending to infinity is there. So Sn tending to 2. That is limit n tending to infinity, Sn equals to 2. Finite. Convergent. Okay? So series is convergent. So you can write partial sum sequence, convergent, limit finite, implies series is convergent. Clear? So similarly, you can test take this question. Here, what? Prove the following series is convergent and find its sum. Okay, so series is solution. Given series is 2 upon 3 factorial plus 3 upon 4 factorial, 4 upon 5 factorial plus, we have to prove it is convergent. Given series is this. Okay, 2, 3, 4, 4, 5, 3, 4, 5 factorial is there. Okay, 4 by 5 factorial is convergent. We have to prove. So given series is this. Here un is equals to we can write n generally start from 1. So we can write n plus 1 upon n plus 2 factorial. So n equals to 1, then 2 by 3 factorial. N equals to 2, then 3 by 4 factorial. N equals to 3, then 4 by 5 factorial. So un equals to this. Now our target is what? Finding Sn. In this case, we know in factorial case, just we can convert it like this: n plus 2 minus 1 upon n plus 2 factorial. Just we do this type of process just for finding Sn. Okay, so Sn finding is not every time simple. That's why we are using test, different type of test, using nth term without Sn. So here finding Sn, we can do like this: n plus 2. So n plus 2 upon, just distribute it, n plus 2 factorial minus 1 upon n plus 2 factorial. Okay, so it can be written also simply n plus 2, n plus 2, n plus 2, n plus 2 cancel. So 1 upon n plus 1 factorial from n plus 2 outside, then n plus 1 factorial is there, minus 1 upon n plus 2 factorial. So this is finally un. Okay, now just we try to find Sn for testing it. Okay, so un equals to this is given. Now we have what? Sn. Sn equals to what? u1 plus u2 plus u3 up to un. So u1, we write this, but in this form. Here n equals to 1. So 1 by 2 factorial minus 1 by 3 factorial. We can see that n equals to 1, then n 2, then 3. So similarly, u2 1 upon 3 factorial minus 1 upon 4 factorial, n equals to 2. So, and similarly 1 by 4 factorial minus 1 by 5 factorial, and up to like this un, last term is 1 by n plus 1 factorial minus 1 by n plus 2 factorial. Now here we see that this cancel, this cancel, this cancel, and so on. Just first and last term will remain. 1 by 2 factorial minus 1 upon n plus 2 factorial. Okay, Sn equals to this. Sn equals to this, Sn equals to this. Since limit n tending to infinity 1 by n factorial is equals to 0 implies limit n tending to infinity 1 by n plus 2 factorial also tending to 0. 1 by n factorial n tending to infinity equal to 0. So limit n tending to infinity 1 by n plus 2 factorial equals to 0. This is a special type of limits. So just use this type of limit. So this tending to what? This is equals to 2 factorial means 1 by 2 minus 1 upon n plus 2 factorial. Now this tending to 1 by 2. Tending to 1 by 2 means this tending to 0, half. So Sn tending to, that is limit n tending to infinity Sn equals to half. Okay, limit tending to infinity Sn equals to half. Finite limit. Partial sum converges. Sequence of partial sum converges. So series is converges. And sum is equals to half. This. Okay. So this implies series is convergent and its limit is half. Limit is half means series, summation of series is half. At sum is half. Okay, limit is half means what? That we can write un equals to half. N finite series 1 to n. So this is its sum. Okay, summation series is convergent and its limit is half. Sn tending to half. So by using this method, the different type of methods, we can test for convergence divergence of the sequence of partial sum. On the basis of this, we can declare the series is convergent or divergent. And if limit is finite, then that is the sum of the series. Okay. So here we use this special type of limit, this type of special limit. So this list of special type of limits you have should remember always. Okay. So here also we can see that this type of series infinitive. What is the nature of this summation degree? Here Sn equals to 2 if n is odd, minus 2 if n is no 0 if n is even. Okay, even then 0 and odd then 2. This first term and third term up to this 2, up to this also 2, up to this also 2, and if even term 0, 0, 0. So if n is even, sum 0. If n is odd, then 2. Okay. So here Sn tending to either 2 or 0, finite. So series is oscillatory. What is given series is oscillatory. Here Sn tends to finite limits 2 or 0. That is, limit is not unique. So series is oscillatory. Series is oscillatory. Okay. So partial sum, always finding partial sum is not possible and very tedious and very difficult. That's why we are using test, different type of test. Okay. Now P series test. So just for testing convergence and divergence, we require what? Sn, partial sum. So it is always not easy for finding partial sum of if series for infinite series. So we will use some test, some special type of test. Some helping series are also there. The test is also available. Just we use that test for determining the nature of the infinite series. Here P series test is helping series, P series test, also geometry series test. So here P series test, just P series test is very useful for finding or determining the nature of infinite series, just like a convergence or divergence. Here P series test, it can be treated as a questions also. So here see, the series 1/1 to the power p plus 1/2 to the power p plus 1/3 to the power p plus and so on, 1/n to the power p plus, this is 6. Okay, 1/1, 2, 3 p power infinite. The series this is convergent. This is convergent if p is greater than 1 and is divergent if p is less than equal 1. Okay, this is first, this is second. Here p is a number which may be greater than 1 or may be less than equal 1. In the case of less than equal 1, this series is divergent, and when p is greater than 1, convergent. Okay, so P series test here. For proof of this, there are two techniques. By using integral test we can prove it, and also in other way we can prove it, because it is important, so it can be treated as a question also. So this series, if we write like this, summation un n equals to 1 to infinity, then we can write here nth term is 1 upon n to the power p. 1 upon n to the power p. N equals to 1, 2, 3, 4, and we can get series. But for this proof of this series, we can use other method also. By taking this series, we can see that this is convergent for p greater than 1. So case 1, if p greater than 1, then we see that if p greater than 1, then we see that this series is okay here. Just take n equals to 1 to infinity equals to what? 1 upon 1 to the power p plus 1 upon 2 to the power p plus 1 upon 3 to the power p. Two terms. Just make group of element, 2 element, then 4 element, then 8 element. Just we want to see that what will be the behavior of this series by grouping like this. 1 by 3 to the power p plus up to just like this, 1 by 4 to the power p, 1 by 5 to the power p, 1 by 6 to the power p, and then take 8 element, 1 by here 3, sorry, here 3, and 4, 5, 6, here 7. Similarly, here 1 by 8 power p, 8, 9, 10, 11, 12 up to 8 term. First 2 term, 4 term, and then 8 term. 1 upon 8 to the power p, 1 upon 9 to the power p, plus and so on, 8, 9, 10, 11, 12, 13, 14, 15. So up to 15. 1 upon 15 power p. And then also do this. Okay, up to infinity. In this series, just we are grouping 2 and then 4 and then 8 and then 2 and 4 and then 8, 2 power 3 and then 2 power 4, 16. Okay, so we can group like this, total series as infinite. Here we see that. Now we see that 1 by 1 to the power p, this first term, 1 by 1 to the power p is equals to what? 1. This 1 by 2 to the power p plus 1 by 3 to the power p. Here p greater than 1. P greater than 1, that means this is less than what? 1 upon 2 to the power p plus 1 upon 2 to the power p. Here 1 upon 2 to the power p, 1 upon 3 to the power p, p is greater than 1, that is this value is larger value than this value. So this 1 by value is less value than this. So this quantity is less than this as it is, and this is less than this. So in place of this we can write this. So this second two terms combination, this is less than this. Here same type of element, so 2 upon 2 to the power p. Okay, 2 upon 2 to the power p. So we can write 1 upon 2 to the power p minus 1. Okay, so first term is this, second term is less than this. Similarly, taking 4 terms. Similarly, this 1 by 4 power p plus 1 by 5 power p plus 1 by 6 power p plus 1 by 7 power p, 4 term. This is less than. P is greater than 1. So this 3 terms is less than 1 by 4 to the power p. So we can write like this in 3 places, 1 by 4 to the power p. So 1 by 4 to the power p plus 1 by 4 to the power p plus 1 by 4 to the power p plus 1 by 4 to the power p. Because this is less than this. This is less than this. This is less than this. As p greater than 1. P greater than 1. So this is equals to 4 times. So 4 by 4 power p. Now we can write 1 upon 4 power p minus 1. That is, we can write, it can be written 1 upon 2 power 2p minus 2. It can be written. Okay. This can be written 1 upon 4 means 2 square. So 2 to the power 2p minus 2. So this. Also 1 by 8 power p, 1 by 9 power p up to 1 by 15 power p is less than 8 upon 8 to the power p. We can write. With this also, this to this. So 8 terms are there. So 1 by 8 to the power p in each places, in these 7 places, we can write 1 by 8 to the power p less than sign. Just similar process. So this is less than 8 by 8 to the power p, and this can be written as 1 upon 8 to the power p minus 1, and this can be written as 2 power 3. So 1 upon 2 power 3p minus 1. Okay. So first term is 1. Second combination is less than this. Third combination is less than this. And fourth combination is less than this. So using this, in case 1, okay. Using this, values, we get, using these values, we get the series this is less than. Using these values, this series this is less than, this is equals to 1. 1. First value. Second value is less than, because series is equals to this, but this value is equal to 1, and this value is less than 1 upon 2 to the power p minus 1, less than. So here we put less than 2 to the power p minus 1, plus this combination is less than 1 upon 2 to the power p minus 2p minus 2. This combination is less than 1 upon 2 to the power 3p minus 3, and so on up to infinity. So we get this. Now total infinite series is less than this type of combination. Okay, so here this value can be solved. This is equals to, this series is equals to, this series is less than this. This is equals to 1 plus this. Less than, here equal means this is equal, but this is less than this. So 1 by 2 half power p minus 1. 1 by 2 power 2p minus 2. 1 by 2 power 3p minus p. This is an infinite GP. This is an infinite GP. So you know formula. What? 1 upon 1 minus 1 by 2 power p minus 1. For infinite GP, sum equals to a upon 1 minus r formula, where r is less than 1. Since this, and here if p is greater than 1, p is greater than 1, so p is greater than 1, that means this is a finite quantity. Okay, so this is a finite quantity. Okay, it is finite. Well, that is, this series is less than finite value. So we get for p greater than 1, series is less than finite value. So we get for p greater than 1, series is less than finite value. Okay, n equals to 1 to infinity. Series is less than finite value. Series is less, sum is less than finite value, that means series convergent, implies summation un n equal to 1 to infinity is convergent. Clear? So for p greater than 1, series is convergent. Okay, this is first part is proved. Now second part, be less than equal 1 or equal 1. So, case 2, first let p equal, because in second case p less than equal 1. So first p equal 1, let, then this series is very, very important. So its proof is very simple, but writing process is lengthy. Okay, so here if p is equal to 1, then series summation even, in this series the summation even is can be written as, just combine like this, 1 upon 1 to the power p 1 plus 1 upon 2 plus, because p is equals to 1, p is equals to 1 means series 1, 1 by 2, 1 by 3, 1 by 4, 1 by n, and so on. So 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, 1 by 8. So here combination, we make this type of combination. Nine, 10, 11, 12, 13, 14, 15, 16, up to 16. Means what? 2 terms, 4 terms, 8 terms, and so on. Just here for combining, these two remain as it is, and here we start from here combination. Okay. Here we see that, just we will discuss now for p equal to 1. So here we see that one plus half. First, this combination, 1 plus half equals to 1 plus half. Okay, this is equals to as it is. Now 1 plus 1 by 3 plus 1 by 3 plus 1 by 4. These two combination. These two value. Here, this can be written as greater than 1 by 4 plus 1 by 4. Why? Because 1 by 4 and 1 by 4 is equal. But 1 by 3, here 3 is less value. That is, this is greater value than 1 by 4. So 1 by 3, 1 by 4. This is equals to what? 2 by 4. This is 1 by 2. Now combine this. 1 by 5, 1 by 6, 1 by 7, 1 by 8. These all are greater than. These all are greater than. This is greater than 1 by 8. This is greater than 1 by 8. This is greater than 1 by 8. So in place of this, we can write 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8 equals to 4 by 8 equals to half. Okay. So this 4 combination is greater than 1 by 8 4 times. So 4 by 8, that is 1 by 2. Similarly, 8th term. Similarly, 1 by 9 plus 1 by 10 plus up to 1 by 16 is greater than how many times? 8 times. So 1 by 16 plus 1 by 16 plus up to 1 by 16, 8 times. So 8 by 16 equals to half, and so on. You can write. Okay. So this is greater than 1 by 2. This is greater than 1 by 2. This is greater than 1 by 2. And this type of combination, you can see that that type of group is greater than 1 by 2. So we can write this series here. Using these values, we see that this series is, here this is as it is and remaining are half. This series is equals to greater than, all values are greater than half. So first two term as it is, and this is greater than half, this is greater than half, this is greater than half, up to infinity. Up to infinity. Okay? Clear? Now from here we can see that as n tending to infinity, because this series 1 by 2, 1 by 2, 1 by 2, 1 by 2, 1 by 2 and so on. So we can write n terms sum n by 2 as n tending to infinity. So what can be written is 1 plus n by 2 as n tending to infinity. We can write because 1 by 2, 1 by 2, 1 by 2, 1 by 2 up to infinite. So suppose 1 plus this is infinite series. So we can make partial sum from n up to n terms. So just make n terms. So n 1 by 2, 1 by 2 n times n by 2, n by 2. Here n tending to infinity. So we can write like this. This is tending to what? Infinity. As n tending to infinity, n tending to infinity, finite plus infinity, tending to infinity. So this is greater than infinity. That means what? This is divergent. Okay. Hence, we get for p equals to 1 series is divergent. For p equals to 1 divergent, p equals to 1 divergent. Now we have to prove for p is less than, also series is divergent. Okay, so second case under case 2. So let's p less than 1, then here for the case p less than 1, in the case is 1 as it is, 1 by 2, p less than 1. So series is this, 1 by p. So here we can use just series as it is. Because this is a big result, very important result. Auxiliary series for testing, P series test. So let p less than 1, then 1 plus 1 by 2 to the power p plus 1 by 3 to the power p plus 1 by 4 to the power p plus and so on up to infinity. As p less than 1, as p less than 1, 1 by 2 to the power p and 1 by 2. What will be the relation in between this? Because p is less than 1. So, this is less value. P is less than 1. So, 1 by 2 to the power p, just p to the power 2 to the power p is less value than 2. So 1 by p 2 to the power p is greater than half. Similarly, 1 by 3 to the power p is greater than 1 by 3. 1 by 4 to the power p is greater than 1 by 4, and so on. We can write 1 by 4 to the power p is greater than 1 by 4, 1 by 3 to the power p is greater than 1 by 3, 1 by 2 to the power p is greater than 1 by 2, as p less than 1. As p less than 1. So we get series n equals to 1 to infinity un. This series is greater than 1 as it is, plus in place of this just write 1 by 2, in place of this just write 1 by 3 and 1 by 4. Clear? And this series is same as p equals to 1. Okay? So this is what? Which is divergent series. Divergent series as divergent series as from the case p equals to 1. Just if p equals to 1, just we have proved that for p equals to 1, this is divergent. So, which is divergent series as from the case p equals to 1. If p equals to 1, we can get this series. This is divergent. So, this series is greater than divergent series, implies n equals to 1 to infinity, un is divergent. Is divergent. So p is less than 1, divergent. Hence proved. For p is less than 1. Hence proved. So this is helping series and also p series test known, well known series, p series test. Whenever we are having a series, just 1 upon n to the power some quantity, then p is greater than 1, then convergent, and if p is less than or equal 1, then divergent. Just like series 1 upon n square, convergent. 1 upon n to the power half is divergent. Why? Here 1 upon n to the power half means p half less than 1, divergent. 2 greater than 1, convergent. So just we can say direct by using p series test. This is convergent, this is divergent. So this is helping series. So this is the proof for this test. Okay. So this is p series test and also helping series for our further test for convergence and divergence. Okay. Now first test is comparison test. Comparison test means whenever we want to test for convergence or divergence of a series, just we take another helping series. Just we have to make a helping series. And the nature of that series is known. Just we take a known series which convergence and divergence can be determined easily by any of the helping series. And just our target is what? Compare the given series with the helping series. So that is comparison test. Okay. So first test, comparison test. Comparison test. Okay. So comparison test, it's a statement, very simple. Suppose we want to test for this series, whether it is convergent or divergence. Just we have to make a series. If we are having a series Vn, two series, and this series is known whether it is convergent or divergent. Suppose this is convergent, and if we are having this series for testing and this is our helping series, if these are two series and un is less than equal vn for all n, un is less than equal vn, then for convergence of this, we know its partial sum, what? From here, un is less than equal vn, that is u1 is less than equal u2, B1, U2 is less than B2, and so on. So its partial sum, what? U1 plus U2 up to UN will also be less than B1 plus B2 up to Bn, and this is partial sum for Un. This is partial sum for Bn. Since if Bn is convergent, then this tending to finite. If this tending to finite, and as this is less than equal this is also finite. So if this is convergent, then even is convergent. So it is our helping series. If we can get a helping series just like this, then we can say that the given series is convergent. If this is divergent, and we are having this type of relation, if Un is greater than equal to Vn and Vn is divergent, then this is infinite. This is also infinite. So because it is divergent, so this is tending to infinite. So it is also tending to infinite because here will be greater than. This is infinite, so its greater value also tending to infinite. So if it is divergent, then it is also divergent. So this is our helping series, and this is the condition. If we are having two series and Bn is convergent and its this relation is there, then Un is also convergent. If Bn is divergent and we have relation like this, then Un is also divergent. It's this is comparative test. Okay, just we have to compare. Its limiting form is important for proving or for determining the convergence and divergence of the series. Here we have to take limiting form of this test. Okay, if we have two positive series, if two series summation Un and summation Bn be such that clear? If two series summation Un Bn such that limit n tending to infinity Un by Bn is equals to finite quantity and not equals to 0. If Un by Vn, if two series, positive term series also, this positive term series means the sum of the term may be negative terms, some of the terms, in the finite number of terms are negative and remaining terms are positive. After neglecting some finite number of terms, all the terms are positive. That is called positive term series. If the series are positive term series and having this, then both the series summation Un and summation Vn together converges or diverges. Converges or diverges. Okay. Then both the series summation Un and summation Vn together converges or diverges. Means together converges means If Bn convergence, then Un convergence. If Bn divergence, Un divergence. So this is comparison test. Okay. So it can be proved very simple by using limit, definition of limit. So proof of it, its proof is very simple. Okay. Using your definition of limit of sequence. Definition of here, using definition of limit, just for every positive number epsilon greater than 0, there exists a positive integer m such that, because it is given limit of this is equals to finite quantity, so let limit is equals to k, finite quantity is k. Say finite quantity not equals to 0. Say this limit of this is equals to k. So using definition of limit, for every epsilon greater than 0, there exists a positive integer m such that modulus of un upon vn minus k is less than epsilon for all n is greater than equal n. This means if its limit is k, then the difference of this and k, this, is less than a positive number, very small number. This difference is less than epsilon for all n except some integers. After some integers, because integers are continuously the value of n, positive integer. After some terms for all, because if we ignore this m terms, because this is true for all n which is greater than or equal n. So before 1 to m minus 1 integers, if we neglect, then we can write this is true for all n. This is from definition of limit. From these, we can write un upon vn minus k is less than epsilon for all n after ignoring first m terms, first m terms of both the series. From both the series, if we ignore first m terms, 1, 2, 3, 4 up to m terms, ignore. Positive term series, we can ignore some different number of terms. So m is existing number. So m terms we ignore. Then for all n, this relation is true. We can do for convergence divergence for infinite series. So after ignoring first m terms of both series, we can write like this. From here, just we have to discuss convergence and divergence. Together converges, together divergence. If Bn converges, then Un converges. If Bn diverges, then Un diverges. This is from definition of limit. From this definition, just we ignore m terms. Then we get this relation. This is true for all n. Now, this term un upon Vn minus k mod is less than epsilon for all n. After ignoring, we can write it. So by definition of modulus, just we can write it. How? Minus epsilon is less than un by Vn minus k is less than epsilon for all n. Clear? So modulus can be break. Modulus can be break. This. Now we can add k in. So k minus epsilon less than un by Vn is less than k plus epsilon for all n. Just we get this relation. Okay. Now we have to discuss about convergence and divergence of the series. So just write here. We have what relation? K minus epsilon less than un by Vn less than k plus epsilon for all n. This k minus epsilon less than un by Vn is less than k plus epsilon for all. Okay. Now we have to discuss about convergence divergence of series. So here our helping series will be second series summation Vn. So take case number 1. Case 1. If summation Vn is convergent, then if summation Vn is convergent, second series is convergent, then its partial sum V1 plus V2 plus up to Vn limit finite set. If summation Vn is convergent, then its partial sum tending to finite number. Partial sum V1 up to Vn is finite number, suppose h. Then from this equation 1, this equation 1 for all n, this is 2. From 1, second part, we get un upon Vn is less than k plus epsilon, implies un is less than k plus epsilon Vn. Okay, this. So we can write this is for all n. This is for all n. So from here, all n means for 1, 2, 3, 4 and so on. So from this relation we can get what? u1 plus u2 plus up to un is less than k k plus epsilon v1 plus v2 plus up to va. We can write this and for all n, so we can write like this also. This implies we can write like direct like limit, also we can take limit and tending to infinity. Because this limit this is constant term k plus epsilon. So limit n tending to infinity v1 plus v1 plus v2 and tending to infinity. Because for all n, un is less than k plus epsilon vn for all n. So just take sum up to 1 to n. Here also up to 1 to n. K plus epsilon is constant. So we can take for all n, so we can take limit n tending to infinity, limit n tending to infinity. This is less than k plus epsilon limit n tending to infinity. Now this is from equation 2. This is what? H. This is this limit. So k plus h equals to k plus epsilon into h. This finite value. H means this. Its limit is finite because it is convergent. So this is finite value. This is h. This h. When Vn is convergent, partial sum tending to finite limit. And from this relation, limit, this relation, we get this implies this. So here this is equals to h, k plus epsilon plus h finite value. So this is finite value less than, this is less than. What is this? Partial sum of the series summation un. Summation un. Limit of partial sum of series un is less than finite. That is finite. So we get limit n tending to infinity u1 plus u2 through un is also finite. Limit this is also finite. Okay. So we get this is also finite. Implies summation un is convergent. Okay. So if summation vn convergent, then summation un convergent. Clear? Similarly, case 2. Just consider case 2. For case 2, as a similar process, we can observe that if Vn is divergent, then limit this partial sum of series summation Vn is infinite. Limit is infinite. Clear? Limit is infinite. This also from 1 we get taking left hand side now, taking this side. K minus epsilon is less than un upon Vn for all n. From here we can see that un is greater than, just write in reverse order, Vn is here, so greater than, un is greater than K minus epsilon Vn for all n. So we can get limit n tending to infinity, this is greater than, here K minus epsilon is this, and this is infinite. Here this is infinite. So this is equals to K minus epsilon into infinite equals to what? Infinite. Infinite. So this limit, that is limit of partial sum of series un is greater than infinite. That is what? So we get limit n tending to infinity un u2 up to un is infinite. Implies this is divergent. Okay. So if this is divergent, then Vn is divergent, then un is also divergent. Clear? Here we use relation this. This comes from where? This limit. So if this condition is satisfied, then both series here converges together or diverges together. Okay, so this is the comparison test. So for using this test, first of all, we suppose some series, that is helping series. Here V will be the helping series. So V can be found, Vn can be found from the un also, because we take a helping series that helps us to determining the behavior of series, that is the nature of series, whether it will be convergent or divergent. So just we will compare, comparison test, that's what I call comparison test. Compare the given series, that is un, with our helping series Vn. First of all, this condition should be satisfied. Suppose we are given a series un, just we suppose, let us we compare this series with summation Vn, and Vn is known. What is Vn? Just you can suppose. And how can you suppose Vn? So Vn can be found from un also. Okay. In such a way that, just suppose Vn in such a way that un by Vn tending finite, not zero number, should be finite and non-zero number. Then we can apply comparison test. This is the condition. This is the condition for comparison test. So for given series un, just we suppose Vn, so that un by Vn is tending to, that is limit of un by Vn is finite number, non-zero. Then we can apply comparison test. For application of comparison test, if this is convergent, then this is convergent. If this is divergent, this is divergent. And Vn can be found from un. If un can be expand, if the value of un can be expanded as a power of 1 by n, as a power of 1 by n. This is the technique. How can we find the Vn for a series? Okay. So if un equals to un can be expanded as a infinite series in powers of 1 by n, then the least power of 1 by n, suppose 2, it can be taken as bn, least power of 1 by n. Okay, so take a question here. Suppose here we are given this. Test the convergence of the following series. Okay, so just we will use comparison test for this. Okay. This is a question solution. Given series is 1 upon root 1 root 2, 1 upon root 1 plus root 2, this, plus 2 upon 1 root 2 plus root 3, 1 upon root 3 plus root 4. This is series. Root 2 plus root 3 plus root 4 and so on. This is given series. Just we have to test for convergence of this series. Okay, so here we have to find first what? un. We can write like this. Here, just first our target is what? Finding un. Here un equals to, we can write un equals to root over n plus root over n plus 1. Okay, root over n plus 1. Then for using what? Comparison test, we can take Vn from this un also. So un from in this we can write 1 upon, this can be written as, just take common root n from this, 1 upon, in the denominator if we take root n common, then we get 1 plus root over 1 plus 1 by n. Okay, root over 1 plus 1 by n, and here 1. Clear? This root n and 1, 2, 2, 3, 3, 4. So un can be written like this. Now for testing of convergence of this series, just for comparison test, we require Vn. So here we can find Vn from un if un can be expressed as a infinite series. So here we just common root n from denominator, just here 1, here root n is common, n is common, then root n, 1 plus 1 by n this. Now we see this 1 upon root n, and this series can be taken in numerator and can be expressed as a binomial expansion. So here we see that first term will be 1, so 1 by root n is first term, and then another term can be getting. So here we can take Vn equals to 1 upon n to the power half, 1 by n. So let us compare just with suppose Vn. So let us compare given series summation un, with the series summation Vn, where Vn equals to 1 upon root n. Means we take Vn equals to 1 upon root n. This is first part, as increasing power of 1 upon n, power half, least power this. Let us compare this series, given series, with the series this, where Vn is this, we write Vn equal to this. Okay, Vn equal to this. Then we see comparison test can be applied if un by Vn tending to finite quantity, not 0. So then we see that un upon Vn, because limit we have to find must be finite and non-zero. So un by Vn, un is what? This 1 upon root n 1 plus root over 1 plus 1 by n. This is un upon Vn, that is divide by Vn 1 by root n. Divide upon divide. You can write it as a multiplication also. So this will be what value? 1 upon 1 plus root over 1 plus 1 by n. Vn equals to un by Vn equals to, because 1 by root, this is un, and divide 1 by root n. So this will be, go to the numerator, this cancel, so 1 upon this is remaining. And this tending to what? Limit n tending to infinity, un upon Vn equals to limit of n tending to infinity of 1 upon this 1 plus root over 1 plus n, 1 by n. This is equals to what? 1. Because n tending to infinity, that is 1 by n, 0. So root 1 half. Sorry, half. Limit is half. Limit will be half. Because what? 1 upon 1 plus 1. Just you can write like this also. 1 upon 1 plus 1 equals to 1 by 2 equals to not 0. Finite. Clear? Equals to not 0. Finite. Okay. Therefore, limit un by Vn and tending to infinity, this is finite and non-zero. So 1 by 2 is limit. So this is condition for comparison test. The series this is compared with series Vn. So we can use comparison test. According to that, summation un and summation Vn will both either converges or diverges. Together converges or diverges. According to that, summation un and summation Vn will both either converges or diverges. Okay. So now it is helping for helping series. Now by using P series test, now by using P series test. Now by using P series test, what is P series test? 1 by n to the power p. If p greater than 1, convergent. If p less than 1, divergent. This P series test. So by using P series test, summation Vn, that is summation 1 upon root n, that is what? Summation 1 upon n to the power 1 by 2 is divergent. Clear? Summation Vn 1 by root n, 1 by n to the power half is divergent, as p equals to half is less than 1. P equals to half is less than 1. So by using P series test, this is divergent. So by comparison test, summation un is also divergent. Okay, so un is also divergent. Clear? So summation un is also divergent because Vn is divergent, so un is also divergent by comparison test. Okay, so this is the technique of using comparison test. Okay, comparison test can be used if the condition of comparison test, that is given by Vn tending to finite limit, non-zero limit, then you can use comparison test. And just given series is compared to the helping series, that is summation Vn, and Vn is so chosen that its nature can be find easily, just like using P series test. Okay, so this is divergent. So given series is divergent. Okay. Now I will give some questions for your practice. Just do all these questions. Okay. Use any of the technique, just whatever the technique, just up to now I have already discussed in this class. So use that concept and try to find the convergence, divergence, nature of the series. Just do this 5-6 questions. Okay. In your copy also note down it and try to solve some more questions also for convergence and divergence. In the next class I will continue by using other technique for testing convergence and divergence of series by with another test. Okay.